All right, well, I'll just go ahead and get started here while we let some people join into the webinar. Start with a little introduction. I'm Carly Sapola. I'm the Director of Engagement for the American Solar Energy Society. I want to thank you for joining us on our monthly webinar series. Before we get started, I just want to update you on who and what ASES is and highlight some of our current events and programs. The American Solar Energy Society, otherwise known as ASES, is a 501c3 nonprofit organization that was established in 1954 and advocates for sustainable living and 100% renewable energy by sharing information, events, and resources to cultivate community and power progress. If you are not already a member, you can join our community at any time at ases.org/join. Our webinar registrants get a special 10% discount on all of our memberships, excluding life, using the promo code webinar. So feel free to head to ases.org/join, use promo code webinar for a little discount. I want to let everyone know that per this little graphic that's up here, we'll be having our 51st annual National Solar Conference, Solar 2022 Energy Transition with Economic Justice in Albuquerque, New Mexico at the University of New Mexico, June 21st to 24th, 2022. We're accepting proposals right now to present at the conference, so please do consider submitting to our call for participation by January 5th. You can learn more and submit at ases.org/conference. The 2021 National Solar Tour did take place in October of this year. All virtual local solar tours and solar sites are still online for you to check out. They will be up until January 15th. So please do go to nationalsolartour.org and check out the 2021 National Solar Tour. I also want to let you guys know to mark your calendar for the 2022 National Solar Tour, which will be October 1st and 2nd next year. I also want to let you guys know we've got the ASES online community. This is a space for our community to collaborate, share content and information and network. We just launched a brand new online forum called Ask a Renewable Energy Expert. Where we have our technical divisions experts on call to help you and help answer questions about anything technical, solar, sustainable, energy efficiency related. We've got James Stalker, who'll be presenting today, who is one of our technical division chairs, and he'll be talking more about that. So be sure to hop online and start engaging at community.ases.org. Thanks so much for taking the time to listen to my ASES updates. I want to note that this webinar will be available in a recorded format. So keep an eye out for the recording and a follow-up email to you guys. It'll be on our YouTube. Please be sure to submit any comments to the chat section of the webinar and any questions to the Q&A. We will cover all questions and comments at the end of the presentation today. So please be sure to throw those in during the webinar. We'll cover them at the end of the presentation. Now I'll go ahead and hand over the webinar to our presenter today, James Stalker, who will be presenting on the topic of how to accelerate global adoption of solar energy using cutting-edge scientific advancements. James?
Thank you, Carly. Appreciate the opportunity to talk to our folks here. Can you see my screen?
Not yet. If you want to click that share screen, you should be able to select your presentation. Perfect.
Okay, so I'm gonna put in the full screen mode. So yeah, thanks again, Carly, for this opportunity. When I talked to you in Boulder, we didn't have any slots available for the year. So thank you for making that happen. So hi everyone, welcome to my webinar. And I'm going to talk about some of the work that I did over many years, which resulted in a method that's going to advance some of these areas that I'm going to touch on. And hopefully that would also advance the global adoption of solar energy globally. So in this webinar, I plan to cover these topics: overview of solar energy adoption, webinar motivation to accelerate adoption globally, and the importance of energy assessment in various phases. And of course, I'll be dwelling a little bit longer on the cutting edge advancement in solar energy and include some examples and top it off with some summary and Q&A, as Carly pointed out toward the end after I finish my webinar. So let me just jump on to the overview of solar energy adoption. I looked a little bit at research over the past week or so. It looks like, when we combine the big three renewable energy sources, hydropower, wind power, and solar power, the relative and absolute percentages of adoption globally, again, some countries do better than the others, like the US and also China and India and Brazil. But globally, overall, if you take those big three, we're talking about 69% coming from hydro, about 21% coming from wind, and 10% from solar, relatively speaking. But if you put that in absolute terms, again, the numbers that I show here are for electricity generation. It does not include heating and also transport. So if we include them all, those percentages would go higher. For example, for solar, that's about a little over 2%. So that's really where we are as far as global adoption is concerned. And these data came from Our World in Data, that they did a summary report using information from various agencies and even the US Energy Information Administration also. So that's really where we are as far as where solar energy is globally. So we have a long way to go. And that's really what I want to touch on in this webinar. So as I pointed out, solar energy has received a lot of visibility globally, which is great. But its adoption lags the other big two sources, hydro and wind. And maybe that's related to the even efficiency. For example, solar energy is in the low 20s, and wind has been in the mid 40s and so forth. So that's something that we could do. There's a lot of research, not only into materials, but other aspects. And there are some challenges, again, to increase global adoption from diminishing market incentives. For example, our own country with the the investment tax credit, for example, is going to be phased down by 2024. So that's not going to help. So overall, investors in utility scale projects, they require robust solar assessment and forecasting capabilities to ensure return on investment. So for example, if it's not supported by some of these incentives, as they're going to go away, investment is going to dry out as well. So that's kind of a concern for us as we push the increased global adoption for solar energy. So I will kind of stop there on that topic, and we'll get to the importance of assessment. So I guess I want to define what solar energy assessment is for some of us. As chair of that division, I have seen not so much interest as it should receive, because it's one of the main topics. It's possible that a lot of the folks actually think that problem has been solved. And that's something that I want to actually shed some light on too. But solar energy assessment is essentially about how much energy you're going to receive at your project site. Now, what you do with it, or how you design your panels and orientation and things like that, that's all fine, that's secondary. Primarily how the energy is reaching your site. And we have to be able to do that for the past periods and also up to current times, and of course in forecasting mode. So there are three phases that are going to critically depend on solar assessment, and that is design phase, includes site selection, and also plant operation when the plant comes online, and evaluation of the projects and the design, and you want to get some feedback to refine your design also. So a good assessment technique or technology or advancement is going to help in all of those three phases. For example, high resolution solar radiation data for the past tens of years are required for robust design, as an example. And similarly, high resolution modeling effort will be needed to capture some of the physical processes I would go into a little bit detail. They're required for accurate forecasting also. So I just want to make sure those who are not familiar with the terminology, assessment really refers to back periods up to current time. So a year ago, 5 years ago, 10 years ago, up to today, that would be called assessment in this jargon, which I try not to use as much, but forecasting is really about what happens tomorrow or a month from now or 9 months from now. So that's really the gamut of the whole effort for assessment. And we have to make sure that we have the right techniques and technologies to be able to do that. So one of the things the models would allow us to evaluate, and you have to constantly evaluate, of course, no matter how good your design is. Once you're done, that's not done. You really need to refine that. And this type of technology is going to help with the feedback also. And I want to talk about one method that I implemented that's hopefully is going to help us, at least the topic of it, not necessarily the technology itself. So I will jump on to the next slide. And I know I just want to give you a little bit of my background. It's kind of important. I'm an atmospheric scientist, now a businessman. But before I went to graduate school for atmospheric science, I was a mechanical engineering student. And I got a master's degree in that, developing some techniques in fluids, computational fluid dynamics. And that came really handy when I went to the atmospheric science program. First received a master's degree and a PhD degree in 1997, all at the University of Alabama in Huntsville. So I guess if I look back my career, I think my roots in computational fluid dynamics actually helped this whole process over the years. And of course, after I left Los Alamos National Laboratory, I ended up looking at wind energy quite a bit. And I wanted to use my skills and my research background in that area. And then of course, I branched onto solar energy also. Now it's more of a, it's a multifaceted, multivariable type of approach. So it's not just wind and solar alone, but it could be really useful to many other areas of planning or design and operation. So what is the motivation for my method is really something that I want to make sure we all understand clearly, because that's very important. The accuracy of atmospheric fluid analysis, and as I pointed out early on, analysis refers to back periods, which is also called backcasting in the jargon, and also prediction, which is forecasting. And you need to really have better understanding than what we are able to right now using the current science. In fact, I will delve into that a little bit more. But before we go to what is that understanding and how to elevate it, it's better to understand what's missing in the current approaches. And I kind of touched on this in border in my talk with only 10 minutes left. It was really not a good job rushing things, but I would spend more time on this aspect here in this webinar, and hopefully we'll have a pretty good Q&A session in the end. So the bottom line really is and I will define it in my next slides, but our current science relies on state variables a lot. And that leaves a lot of data gaps. And that's something that this technique is going to help us fill. And so that's where the accuracy and the robustness comes from the method. So now this is a slide that I want to spend quite a bit of time on because this is a critical thing for this whole technique or the technology and the method. So as I pointed out, state variables, those who are not familiar with the science or not into it as much as some of us, state variables really tell us about the state of the atmosphere. Like if you measure wind speed, temperature, relative humidity, these are some of the state variables. So you're measuring them. There's nothing wrong with it. That's really how we understand the system. But if you really go down that path alone, then you have to measure at every location and every time period, which is really not practical, even for the back periods up to current time. So if you look at that, again, I will go into that a little bit more. So those are the state variables like wind speed. They are not telling you when you measure it, what kind of physical processes led to that particular state variable. As a matter of fact, solar radiation reaching the ground could be considered in this vein a state variable because it does not tell you what type of processes it really undergone in its path to the surface. So the clouds of different kind, maybe different layers, different types of hydrometeors, all of those things would really, impact the solar radiation reaching the ground. But when you measure that, it's not going to tell you what those processes were. There's no way of backtracking. And that's not only for solar radiation, but temperature, wind speed, and things like that. Why is that important? That important difference is when you measure a state variable and you are extrapolating or interpolating to a location where you don't have measurements, you need to have that information about the processes. Otherwise, you will be overestimating or underestimating or creating a lot of bias that you would not be able to quantify. So that's why this is a slide that I want to spend more time going back to maybe in the Q&A session, because the distinction between state variables and physical process variables is really important. So what's the Stalker method is about? It's really about the physical processes that I just mentioned, in addition to the state variables. So I'm not doing anything special as far as getting the state variables. So I don't really have a measuring instrument or a satellite or anything like that. I do get the data that's available from any type of public source or even private source or a combination. But what I do with that after interpolating, extrapolating to the grid that I create within my model, and then let the model actually build these physical processes during a simulation period, which is highly intensive, computationally speaking, but it is allowing those influences to be on those state variables, including solar radiation. So one of the main things about this technique is using a horizontal resolution of 1 kilometer on a side of the box. So those who are not familiar with modeling, 1 kilometer is referring to the side of the box, or 1 square kilometer for the entire area of the domain. And this allows me to create the processes that are relevant. I'm not saying I'm going to be able to capture all of them, but I'm going to capture most of the relevant processes, unlike any other method out there right now. So, and I'll touch on the gaps issue a little bit further down. But so that's the start for the Stalker method and why the 1 kilometer resolution is such a critical piece of that whole puzzle. And of course, you really have to do or know what to do with the 1 kilometer resolution. So running a model at 1 kilometer resolution is really not going to give you a lot of results other than probably using a lot of CPU time. So, okay, so in addition to the deficiency of physical process capturing ability I talked about, that leaves a large data gap too in the assessment or the back period part. So let me give you an example. When you have a 12 kilometer resolution data set, as you use that data to interpolate to a high resolution grid at 1 kilometer resolution. So if you don't consider those variables that are interpolated to a high resolution grid like 1 kilometer, all of those data sets or data points that you're creating, they're based on some type of interpolation, extrapolation, but they're not really truly representative of the location variables as if you measured them. And that's the reason why even if are able to interpolate a 12 kilometer data set, input data set to 1 kilometer resolution, you cannot consider those values that are created based on this 12 kilometer data set to be actual data because of the physical process influences or lack thereof. And that's why if you take a look at, say, anything coarser than 3 kilometers as the input, and you're interpolating or extrapolating to 1 kilometer resolution, creates that 90% data gap. And that's usually the case if you go to any of the models. Some of the climate models are actually in the tens of kilometers, if not over 100 kilometers. So think about their ability to capture the physical processes. That's really nil. And that's really the problem that I see for some of the climate modeling work too. But back to our solar assessment piece, I have seen over the last 15, 20 years, I have been, actively involved in renewable energy. There is a lot of sophisticated design that's happening, which is great. I have nothing against it. That's really great. But the upstream values that go into that design, that is the assessed values for solar radiation reaching the ground, they have that inherent deficiency. That's why we need to go upstream a little bit as an industry to address this problem, to overcome that deficiency and then increase the global adoption. So I hopefully have given you enough background here so we could rethink about, why we jump into sophisticated design than actually address some of the fundamental issue by going a little bit upstream, as in the case of the industry. So, there are three things that I believe we could address with a method like this and the technology built based on that method. So we always have questions like, I picked a location, but it's underperforming, okay? Or you picked a location, but there is a lot more energy available than your design. And also, your forecasts seem to be incorrect all the time, pretty much. That's consistent. And the reason for those, the answers lie for those questions really go back to our inability to capture those physical process influences that I talk about, which are missing in the current science. And unfortunately, I call the current science a state variable science because that's exactly why we rely on it. And there's a reason for that. And I'm not naive to think that there was computing available back in the day. There wasn't. A lot of it was conceptual in nature. They did a lot of great work back in the day with the little computing they had. But what happened though is, as computing took off, we kept on the legacy methods. And that's one reason why I think we're not where we are supposed to be. And hopefully I'm going to change that with this technology concept for the global adoption. So I will jump into some examples here with the time that I have, and I want to leave quite a bit of time for Q&A in the end. But let me jump into this. The example that I'm going to show is for El Paso, Texas. It was part of a study that I did for air quality, Mexico, US border region. And there were always issues about, Mexican cities were polluting US cities, and US was saying, well, it's the other way around. So we wanted to kind of get to the bottom of that. So these are the simulation that I did for that particular work. It's a 1 kilometer resolution model setup. There are 3 grids, and the innermost grid has 1 kilometer resolution. The model depth goes over 20 kilometers with the various levels, very high resolution in the first couple of kilometers to capture some of the boundary layer processes, but also fairly good resolution throughout the depth. And a method like this with the ability or with the interest or focus to capture some of the fast changing cloud processes, I use a time step of about 2 seconds to ensure computational stability. And each initialized simulation only is run for about 3.5 hours. And the last hour of that simulation from the initialization is used and kept. Essentially, the first 2.5 hours are the output is thrown away, which is a significant cost. But during that time, there's a lot of adjustments that are happening from the physical processes. So you get to see a lot of variability, spurious variability that you do not want to rely on. So that's why the 2.5 hours to throw that away as the overhead is an important piece of this technique. So in order to get to 1 useful hour, we have to spend 2.5 hours of simulations and throw them away. If there is a better way to get to the last hour, we would do so, but that's really not how the fluid behaves. So that's one of the main features of this technique. And that's how we're able to capture the influences of the physical processes on state variables. Again, I'm not going to give everyone the physical process interactions and so forth. That becomes more of a scientific discussion, maybe publications and things like that. But in the end, people still want to know what the solar radiation is reaching the ground. They don't have to know all of the processes that radiation went through on its path to the surface. Just because they don't want to know or they don't need to know, we do have to include all of the processes. So there's a lot more information this technique creates that's really not needed for the end user, but the robustness and consistency and accuracy of the methods would rely on this technique because they are influenced constantly throughout the 3.5 hour simulation time period. So I will share a few slides here, and then I think open up for Q&A. So this is the El Paso area. We have the Franklin Mountains just say in the middle of the screen to the north, and there are Juarez Mountains in Mexico to the southwest, with the pink reds kind of separating those two mountain ranges. And you could see the low temperatures found on top of the mountain ranges. And the airport, El Paso Airport, is somewhere in the orange area to the east, smack in the middle of the screen. Not in the screen, but to the second half, the right half, and the middle of that right half in the orange section. I wish I had a pointer to show you that, but this is a simulation using the technique after throwing 2.5 hours of the simulation and then retaining the last hour. And that's really what we're seeing here. And I will be showing a few other slides for the same time. So same domain, so you would know how all of those variables are simultaneously getting affected or influenced for robustness and accuracy. So here is the wind speed for the same time period, same location. As you would see that wind speed is increasing over the tops of the mountains. And then there is some blocking, as you would see on the west of the Franklin Mountains, and a lot more structure, because of the 1 kilometer resolution here. So if somebody is interested in doing a hybrid system, they would have to contend with clouds or presence of clouds over mountain tops that would definitely reduce the solar radiation reaching the ground. At the same time, it has higher wind speed. So you would have to find a location where the hybrid systems are more efficient somewhere other than where there's a lot of wind or there's a lot of solar radiation. So this type of approach and the advancement is going to help maximize those hybrid systems also. Jumping onto relative humidity, it's coming from the same simulation, same physical process influences. And they influence, of course, I don't have to say this, but just want to make the statement that all the physical processes influence different variables differently. And that's really the point. We don't really know how those influences are for variables, particularly for solar radiation, which I think I will get into next. But this is the relative humidity. Again, you would see a lot of structure. And this is only for 1 hour. If you want to do it for a full year or 30 years, which is what I recommend for a large project, it requires a lot of effort. So, and then this is precipitation, not a lot here in millimeters, very little. One would call it a trace amounts, but they influence solar radiation quite a bit, which is what I'm showing you here. If you didn't have 1 kilometer resolution approach, using the type of approach that I have talked about, capturing this type of precipitation amounts and the structure would not be easy to do. As a matter of fact, I would say it's impossible to do. And that means the influence of such precipitation, which again, by definition, that reaches the ground, but you would have clouds also in upper layers. So those influences on solar radiation are going to be critical in assessing what solar radiation is, not only for back periods, but this technique works in future settings also. So let me show you the solar radiation reaching the ground in watts per meter squared. And that could be converted into energy density also in the standard format per day. when we have all of the hours simulated like this. So you would see that the influence of precipitation, obviously, influencing or diminishing over the tops of the mountains where you have cloud presence also. And this type of variability is not really possible using satellites or some of the numerical weather prediction modeling techniques that are being used, because they are not using the high resolution to be able to capture the physics, but they're also using the model output during the adjustments and also running the models over a longer period of time, where it actually hurts the simulation more than it helps. And that's what the key features of my method are. So I'll jump into just the summary part, and I won't spend a lot of time on this, so we will have enough for the Q&A. So I presented some results of 1 kilometer resolution run for 2012. I actually did 3 separate years for the air quality work, 2011, 12, and 13, because we wanted to see how the variability of the air pollution would differ for those 3 seasons. The seasons that we analyzed were May through September. And unfortunately, we didn't really quite finish the work because I found a lot of issues with the other aspects, like the emission modeling. And we didn't quite get to the coupled air chemistry modeling, although my meteorology part was pretty solid. So it wasn't happy when the project didn't go forward. But enough of that. But very strong sensitivity of solar radiation to clouds and precipitation, as I've shown in one example, and physical process adjustments and their influences are important, actually the central feature of the method. And that's why running the model and also the other things I talked about are important to develop robustness and forecasting accuracy. And once we have this, solar radiation determined for each hour and adding all that to a year or 30 years, whatever the case might be, we will be able to ascertain or determine empirically what the direct and diffuse components are. And there are lots of different ways to do that. Some are more accurate than the others, but there's a lot of empirical work that has been done. And I don't intend to do a lot of the work other than choosing the right methods that are available out there. So I think, that's kind of like the summary. But let me just say that if we rely on state variable measurements, which has been the science for the longest time, we're still looking at that 90% data gap. And if you don't bridge that data gap, our ability or inability to capture the processes really suffers. And that's really kind of a key thing. And also, no matter how sophisticated we get in our measuring techniques and also instrumentation, we're unable to measure the future periods in the mode of forecasting. So that's why robust techniques are important, and hopefully that would really help global adoption of solar energy, which really is not that much. If you think about it, there's a lot of visibility, which is great, but we are really at a small percentages, and there's a whole lot of room to grow, and hopefully we could do that. And that's really one of the things I want to bring to this this group and the society, and also hopefully globally. So I will actually kind of stop there. Maybe I finished it in a couple of minutes early, but I think we have plenty of time to do a Q&A.
Yeah, wonderful. Great. We've got some questions coming in. One from Drew Gillette about an earlier method that you had talked about in your presentation. He asks, is there any chance that this method works for fog prediction? NOAA aviation fog forecast could use a better model.
It absolutely does. And but there is some additional work that needs to be done. As a matter of fact, my work began in the severe weather area. I ended up actually simulating multi-cell thunderstorms at 100-meter resolution back in the mid to late 90s. Everybody thought I was nuts trying to do that, but that's the kind of thing that needs to happen for the fog simulations. But I think it's doable. The technique actually works. It needs to be, of course, implemented, but I think the technique is solid enough that it will work for that application also.
Wonderful. A question here from Dave Renee. Isn't this nested modeling approach exactly what WRF offers? How is this method different from WRF being used as a nested model in the NWP models?
Well, from the modeling perspective, Dave, they are all the same. So the model that I have implemented my method at RESPR, that's the RAMS model from Colorado State University. They don't really have any unique, capabilities compared to one or the other. So we're for RAMS or everything else. But the method that I implemented, I chose to do that in RAMS because I used that for my dissertation work. But that method is not available anywhere else, including RAMS, of course. It's my own version of RAMS, and that's why WRF model or anything else, or if you run RAMS, it's the same thing because you're not really utilizing the high resolution feature to capture physics, but also the integration time limit, which is really a critical piece of this. As a matter of fact, I'm writing another paper which hopefully is going to touch on some of those things. But unless you have those criteria and do it, then it's not going to produce anything. As a matter of fact, if you run a model at high resolution over that integration time limit I talked about, it's actually going to make your work less accurate because of the advective components coming into your high resolution. So that's something that it's missing in the science. I'm not picking on them, but that's actually a deficiency. So it's really not the model itself. Models have their deficiencies, and some are better than the other in some ways. I don't want to argue about that, but it's really the overall approach to simulating is really not there. And we'll start with the 1 kilometer resolution first, but then you have to also have the adjustment period and also the integration time limit. Those three are not available anywhere until I actually came up with those. Great question though, Dave.
He's got a follow-up to that as well. As a follow-up, high-res NWP models like WRF provide similar maps that you have shown. Can you demonstrate if the structure you present is more accurate spatially than WRF and NWPs? Also, what improvements does this method offer over satellite-based solar techniques, which are being widely used by the solar industry and offer resolutions of 1 kilometers?
Okay, so doing the one-on-one comparison, I think that's doable. We could do all day long with the other models, but again, how you are setting up your model and are you observing the adjustment period and also the integration time limit, which is really the critical part. All of the models miss all three. So they actually And that's why, I mean, we can demonstrate that for sure. But as far as satellite data, the three-dimensional effects, Dave, for clouds, they're not captured. And if you have like layered clouds or mixed phase clouds, those are not. I mean, you have to make a lot of assumptions about that. There are empirical ways to do it. As far as whether this is going to be better or not, I mean, that's something that we have to do. And I have done that for, some locations. And I'm not saying it has been extensive, but the soundness of the approach, going back to the physical processes, even though some models actually use physical parameterizations in their runs, they're violating these three aspects that I talk about. And that's why they actually produce lesser quality data analysis and forecasts. And I think I have shown that in some locations, but as a scientist myself, fairly robust one, I don't think it's enough to have just some, but I intend to do it a lot more over a lot of different locations.
Great. We've got another question here from the audience, a Robert Foster. Is your model used by any existing solar or wind farms to predict power output generation? If so, how good has it been in predicting output?
Okay, so currently, no. But I have used my technique for a wind farm in Texas. And Robert, that's a great question. When this operator came to me and said, Dr. Stalker, I can get daily forecasts from number of people, vendors, but can you do a 6-month forecast? And I was like, what? I'm not gonna do 6-month forecast at my resolution. He said, well, that's going to be quite useful to me. So I attempted it one time, 6-month forecast. So I gave the forecast at 1 kilometer resolution in hourly data from April 15th to October 15th. And because I did not do that before, I reluctantly told him what my error stats might be. And I was doing better than what I projected. So that's all I would say for that. But right now, my focus, Robert, is not really about a particular industry. The impact of this technology and the method are for multiple sectors simultaneously. And that's why we're trying to do maps for entire states and countries. And all of the projects and other industries within those sandboxes, they're going to benefit from that. So that's my focus. And although I was focusing on renewable energy project developers and operators early on. So I hope I answered your question more accurately there, Robert.
Wonderful. Those are all of the questions that we had incoming. Do you have any other comments or clarifications for our webinar audience before
well, the thing to do is, one of the main points, I mean, from my perspective is, let's not assume or become complacent that the assessment piece has been settled, we are all good, and then jump into sophisticated design. I think we have to back up a little bit and go upstream. And that's a point that I want to really go back to quite a bit. In fact, I'm going to emphasize that in my term as the chair for the next year or so, because that's really where a lot of the issues have been kind of pushed under the rug. And we have to kind of say, hey, we need to look at that. And global adoption, I think, is going to probably get better than where we are now. But that's one point I would leave everyone with as a part of my presentation today.
Wonderful. Thank you so much, James. And again, as a reminder for all of you on the webinar and who might be watching this recording, we have the ASES online community. James is the technical division's chair, so please do log in. If you have any comments for him or questions, you can use that outlet. I'll also be following up with everyone once I get the recorded webinar online with James's contact information as well. If you need to get in touch, we'll look forward to having James as a part of the webinar series in the future as well. So if you have any ideas for what you'd be interested in hearing more about from James, please do let us know. So with that, I'd like to thank you, James, so much for joining us on the ASES webinar series. And we're so thankful to have you in our community.
Thank you so much, Carly. I know all of you folks really work hard, and I was impressed with the first meeting I ever attended in Boulder. Robert has been bugging me about getting involved for many, many years. And I was like, nah, I don't want to do that. But I'm glad I did, because you guys are actually great. And hopefully I could, support it in my own way.
Yeah, and you've been very, very, very supportive. So thankful to have you in our organization, and thank you so much for your kind words. We're going to be in Albuquerque next year, so we'll look forward to seeing you there, James, as well as you guys on the webinar and the ASES membership and broader community. So thank you all so much for joining our November webinar. I'll follow up with you all, so look out for an email from me. And thank you again, James. Thank you, everyone. We'll see you next time.
Thank you so much.
Bye, everybody.